Hi, welcome to another edition of Ordinary Differential Equations. Today we are going to look at some advanced issues related to discontinuous forcing functions and inverse Laplace transform that include a reference to a step function. Let's go ahead and take a look at this story. So, discontinuous forcing functions, we have talked about this thing before, that it's quite often that you have a voltage coming into a circuit and the voltage goes through switches and changes its shape or form. The question is, how would the circuit respond to this? We had seen that step functions are used to model the situation, so it is not surprising that inverse Laplace transform in these situations connect to step functions. Let's go ahead and start by a practice problem, and then we'll have a more complete statement of a problem. So suppose I ask, what is the inverse Laplace of, say, exponential of minus 3 pi s over say s times s squared plus 1. This is a problem that has several layers, and it's going to tell us a variety of techniques and such. And it's all built on that very important formula we talked about several times so far, which is Laplace transform of a switch function at times c times a delayed function by c seconds is equal to exponential of minus cs times Laplace transform of the original function f itself without that delay. So when we look at the expression like this, that exponential has to remind us that there is a switch and delay to be careful about. And then there is a secondary component which has to do with the original function f of t that you are supposed to construct with a capital F of s. So to answer this problem, first we have to go ahead and detect what is f itself. Detection of c is easy. Detection of c is just a number that's multiplying s 3 pi, so I know my c is 3 pi, so that was the easy part. But what is my f? So we go to a secondary problem where we remove this exponential. We just have this expression, s times s squared plus 1. Okay, so if we go ahead and look at our table, we said here a table we made long time ago. The expression that we have doesn't show up in our table, and we said the biggest tool in this approach is to apply a partial fraction decomposition such that your resulting functions are small enough to show in the table. So I go ahead and we want to answer what is this. We still have to open this one up to another one, which is, well, what is the smaller fractions out of which this one is created. So that brings us to another problem from calculus, which is partial fraction decomposition. What is the breakup of this fraction? Well, obviously the denominator is going to have the factors that we have here. And do you remember from calculus, what was it that was showing up on the numerator? How did we do partial fraction decomposition? Try to remember what it was and then rejoin the lecture. So the story was that if the denominator is a linear or a power over linear, the numerator is just going to be a number. And if the denominator was a irreducible quadratic or a power of such thing, the numerator would be a linear expression. That means like bs plus c. So next stage of this game is to figure out what is A, B, and C, and once we have that, we have our partial fraction decomposition. And sometimes you have to go one more layer and take this fraction also and separate it into two pieces, one for sine and one for cosine, and then you're done. Typically, advanced problems in this section turned out to be rather lengthy, so you want to be prepared for that. So what do? We take the common denominator and then set it equal to numerator here. So I want 1 to be identically equal to a times s squared plus 1, and then s times bs plus c. So I want 1 to be equal to, so I collect my expression. I have s squares, and then I have s's, and then I have all the leftovers. So s squares, what do I have? I have a here, I have bss, that's bs squared, so that becomes a plus b. A times 1, that doesn't have any s's in it, so I put it separately. S times c, well, there's just a c here. So there are not that many pieces here, and therefore our problem is not so complicated. A plus b therefore had to be like, there's no s squared here. If you wish to insist to see what's on the left hand side, well, there's no s squared and there is no s, and if these two terms, these two expressions want to be identical to each other, after you simplify them, then the coefficient of corresponding terms have to be equal to each other. So a plus b has to be 0, c also has to be 0, and a, the only term left here, is to be 1. Well, this is extra easy. A is 1, c is 0, and therefore of course b is minus 1. So we got the following, that 1 over s times s squared plus 1 breaks up to a over s, that was 1 over s, plus b is minus bs, it was bs, so it becomes minus s over s squared plus 1. So if I want to calculate the Laplace inverse transfer of this, that is same as inverse Laplace of 1 over s minus s over s squared plus 1. Well, these are things that do show up in our table. If you want to break it up, well, that is easy. You break it up, and now each of these two show up in our table. So what is inverse Laplace of 1 over s? Do you remember what that one was? So for 1 over s, of course, we have just, let me see, maybe you want to think about this thing yourself. What was the inverse Laplace of 1 over s? Try to remember, rewrite the entire table as many times as it takes for you to memorize all these basic ones. And then what was it for s over s squared plus 1? So that one also you want to be having it in your mind ready to go. So sorry, I made an extra section there. So 1 over s, that was 1. Now the other one that we are looking at is s over s squared plus 1. So that's just b is 1, and we are looking at just cosine of t. So let's go ahead and therefore put so 1 over s, that's just 1, and this one is just cosine of t. Okay, so let's see what the problem was. The problem was, what's the inverse Laplace of this? He said put aside the exponential. Go ahead and figure out what's the inverse Laplace of whatever is left. Who is that? That is f of t. Can I just write it just like that here? Well, no. Remember, you have to delay it by these many seconds. And what is this c? Well, the c you see here is just 3 pi. This is c. 3 pi by itself is c, not the minus. So what do I have to do? U of c, so I'll have the u of 3 pi and then times f of, so this is my function, I have to delay it by c, which is 3 pi seconds. A constant, if you delay it or don't delay it, it doesn't make any change to it. It's the same constant. So delayed version of 1 is just 1. Delayed version of cosine of t is cosine of t minus 3 pi. Oh, 3 pi is a very special number, so you can simplify this expression, but I recommend leaving it alone so that we avoid other confusions. Let's remember that this does match that delay, so that's important that they are the same thing. Okay, so that's how we go about doing these problems. Once again, if you're doing with inverse Laplace of something with an exponential in it, the exponential tells you what's the switch and delay time. You put that aside, you look at the rest of the problem, you find the inverse Laplace transform of that, and whatever this thing is, you have to still delay it to get your correct answer. So you have your switch here and your delay here, and very common mistake is to forget this one. Okay, now let's go ahead, look at a problem that has additional layers to it, not just find the inverse Laplace transform of it. So what was it that we want to talk about? We want to look at problems where there was a discontinuous force involved in the statement of the problem itself. So let's go ahead and take a look at an example of this, a problem we had seen before, but we didn't solve it completely. So suppose we want to solve an initial value problem with well, let's use the letter u, that is favorite of the textbook. So u double prime plus u, so this is a system with no damping, and here is the discontinuous forcing function. On the right hand side, perhaps it's 1 all the way up to time 3 pi seconds, say, and after that we are removing this, and after 3 pi seconds right hand side is 0. We said this is reminiscent of a problem like this, that you have some spring attached to a pan, and in this pan you have some weight, and the system is oscillating with this, but at a certain time perhaps you just yank this thing away and that weight is no longer there. What would happen to the oscillation in the system? Well, we need some kind of initial conditions, so let's go ahead and write something for this problem. u0, suppose is 0, u prime of 0, say it is 1. This whole thing, an ODE with initial conditions, we called it an initial value problem. IVP, initial value problem, is something we study here. Okay, so what's the approach? Step 1, write this thing in step function notation. So I go ahead, this whole thing, let's call it f of t, the external force. So what is f of t? F of t at the beginning is just a 1, plus we have a switch at time 3 pi. What happens at that time? We are turning on 0, turning off a 1. So it's simply 1 minus u 3 pi. Not too complicated, so easy to handle. So now I have the following. I have u double prime plus u is equal to 1 minus u 3 pi. So what should I do with this thing? Well, I take a Laplace transform of the whole thing. So I'll have a Laplace transform of u double prime plus u is equal to Laplace transform of 1 minus u 3 pi of t. You remember this breaks up, so Laplace transform of u double prime plus Laplace transform of u is equal to Laplace transform of 1 minus Laplace transform of u of 3 pi. Now I'm in a bit of a dilemma to make sure that my uppercase u is not going to be confused for a lowercase. Perhaps letter y would have been my original lettering would have been better, but let's go ahead. So this is going to be s squared Laplace transform of u, let's make it super big, minus s u of 0 minus u prime of 0, and that this is Laplace transform of the function again, is equal to Laplace transform of 1, which is 1 over s, minus Laplace transform of u of 3 pi, exponential of minus 3 pi s over what? Do you remember what's the inverse Laplace transform of that one? That was just s here. So u of 0, luckily it's just a 0, so one thing out of our hair, and this is just a 1. So these two become, let's take a common factor of u, the Laplace transform of a little u. So I collect these two. This one in the problem was stated to be 0, I believe, yes, and this is a 1. This is a 1, so I can take it to the other side. So I'll have a 1 plus 1 over s minus exponential of minus 3 pi s over s. Now I divide by this, so u becomes 1 over s squared plus 1 plus 1 over s times s squared plus 1, and then finally minus exponential of minus 3 pi s over, same thing, luckily is the same denominator. So this is the Laplace transform of little u. I want to find u of t. Well, we have some work to do. First piece of this thing is straightforward. Okay, so let's see which one of these things we can easily say. 1 over s squared plus 1. Do you remember what is the inverse Laplace of that? That should be easy by now. Inverse Laplace of 1 over s squared plus 1. Stop this, and again, if you forgot, force yourself to rewrite that entire table one more time, from left to right and right to left. Really, you have to repeat it that many times for it to stay in your mind. Then rejoin us. So in that table, this is just sine of t. Well, luckily we have done these problems already, so that the problem doesn't look that long. 1 over s squared plus 1 times s. The inverse Laplace of that was 1 minus cosine of t. So we have to do all of that work, of course. So this is 1 minus cosine of t. And this is that problem we just did at the very beginning with the delay in the switch, which is, this is exactly this answer. So I'm going to rewrite that. So let's write, I write it 1 minus cosine of t minus 3 pi times u of 3 pi. Using the notation of u, and I realized wasn't a smart thing on my part, because u was reserved for the step function. So so long as you realize what's happening here, so the notation here, I didn't want it to collide with the notation there, So maybe we go ahead and change everything to what I had at the beginning, and then I tried to go with the notation of the book, and I got myself into troubles here. So let's use the letter Y. This is going to look silly, but otherwise I'm going to be leaving you with some confusion as to what happened. So this is Y. Not to be, the issue is that we don't want to confuse this with that one. We don't want to have same letters show two different things. So in textbook with their fonts they can manage this thing, but with the handwriting it's not easy to do with the handwriting. So sorry for that. So what we have here is exponential of minus 3 pi s. So it becomes u of, so this is going to be little u of 3 pi. That's a step function. Okay, now we can see some simplification happens here because of some lucky coincidences. You can use trigonometry to simplify that, but that's all essentially accidental. There isn't much significance to it, so I just leave it like that. Now in problems like this, how do we know what is the graph of it? Drawing it by hand typically is going to take quite a bit of time, so we said smart thing to do is to make use of Desmos. So let's go ahead and remind ourselves how do we do this thing again. So we go ahead and define our step function. So the step function here, t less than 0, that's the domain of the function. When t is less than 0, the value of the function is 0. For t that's larger than 0, the value of the function is 1. So it's important you give an inequality and then you give a colon and the formula that applies for that section, and then another inequality and then colon the formula that applies to the new section. You separate these things with a comma. So that is how our step function goes. Let me show you how the step function is looking again. That is how the step function looks like. Up to 0 is just 0. After that it jumps to 1. Then okay, we figured out what's our step function. We go ahead, define our function. Our function had a sine of t, so I have it here. 1 minus cosine of t, I have it here. And then minus 1 minus cosine of t minus 3 pi, all of it is here. Then times the step function at time 3 pi. We said on Desmos you don't have u sub anything. You have to use the shifting notation to have a step function that kicks up at time 3 pi. You just take your u of t and then you subtract that new time from it. It's going to shift it to the right. And what does the function look like? Well, in this case it looks like this. You notice at the beginning there is a small amplitude, and then at a certain time, it has to be 3 pi time here is causing this. It kicks into a new kind of oscillation. So this is a relatively simple problem for this kind of situation, but more complicated problems follow the exact same style, and you should be able to do all of them without any problem. Okay, I hope you followed what happened here. This is an important example, and sorry for that mess for the notation. Until our next meeting, good luck and God bless.